Hello and welcome to Lecture 8. This week we're going to continue our study of the Laplace Transform. We'll start by using the Laplace Transform to solve some more initial value problems. In many ways, this section will be revision of the ideas from the last lecture because that was 2 weeks ago. And then the main part of today's lecture will be in section 4.4. We're going to start talking about step functions. Let me start by reminding you of some of the ideas from 2 weeks ago. Let's suppose we have a differential equation that we want to solve, but let's suppose it's too difficult to use our previous methods. What we can do is we can take the Laplace transform of our difficult differential equation and we can change it into an easy equation for capital Y. If it's an easy equation, we can solve it and we can find capital Y. If we can then find the inverse Laplace transform of capital Y, then we have small y, which is the solution to the differential equation that we started with. Yes. And the reason that this works is due to this theorem. The Laplace transform makes derivatives disappear. It eats derivatives. The Laplace transform of f prime is s multiplied by the Laplace transform of f minus f at 0. And if we apply this equation 2 times, we can find the Laplace transform of f double prime. Or f triple prime if we use it 3 times, or if we use the first formula n times, we can find the Laplace transform of f to the nth derivative. Okay, let's do an example. Use the Laplace transform to solve y double prime minus 3y prime plus 2y is equal to cos t with the initial conditions y of 0, 0, y prime of 0, 0. This is actually an easy differential equation. We could have solved this one using the methods from the previous chapter, but I want to solve this using the Laplace transform. The first thing we do is we take the Laplace transform of the differential equation, and we use the formulae from the theorem. In green, we have the Laplace transform of y double prime, s squared capital Y minus s at y0 minus y prime at 0. In orange, there's the Laplace transform of y prime, that's sy minus y0. In red, the Laplace transform of y, just capital Y. And in blue, there's the Laplace transform of cos t. You will recall that that's s over s squared plus 1. Both of the initial conditions are 0 here, so we can forget about all of these terms. On the left side, we just have s squared minus 3s plus 2 capital Y is equal to s over s squared plus 1. Divide both sides by s squared minus 3s plus 2, and we have a formula for capital Y. To be able to find the inverse Laplace transform of capital Y, we're going to need to use partial fractions. Capital Y must be something over s squared plus 1 plus something over s minus 2 plus something over s minus 1. And what are the somethings? The somethings are always a polynomial of degree 1 less than the polynomial on the bottom. So in the first term, we have s squared plus 1 on the bottom. That's a second degree polynomial. On the top, we should have a first degree polynomial. S minus 2 is a first degree polynomial. So on the top, we should have a 0 degree polynomial. In other words, just a number on the top, and so on. Put everything over the same denominator, and then we can find A, B, C, and D. And I'm going to leave it to you to check my calculation. Check that here we need to have A is 1 over 10, B is minus 3 over 10, C is 2 over 5, and D is minus a half. So capital Y should look like this after we've done partial fractions. I want to write this in a form that we can of terms that we can find on our table of elementary Laplace transforms. So I'm going to split it up like this. 1 over 10 multiplied by s over s squared plus 1. Because s over s squared plus 1 I can find on the table of elementary Laplace transforms. And then minus 3 over 10, 1 over s squared plus 1, I can find that on the table. Plus 2 over 5, 1 over s minus 2, I could find that. Minus a half, 1 over s minus 1. I can find 1 over s minus 1 on the table of elementary Laplace transforms. This is actually 1 over 10, the Laplace transform of cos t, minus 3 over 10, Laplace transform of sine t, plus 2 over 5, Laplace transform of e to the power 2t, minus a half, Laplace transform of e to the power t. And once we've got to this point, we're almost finished. So as soon as we've got to this point, we can write down that small y must be the inverse Laplace transform of this function. So small y must be 1 over 10 cos t minus 3 over 10 sine t plus 2 over 5 e to the power t minus a half e to the power t. And I can show you a graph of this function. This is the graph of the solution to this initial variable. Remember the initial conditions. Y of 0 is 0, so it goes through the origin. Y prime of 0 is 0, so the slope at the origin must be 0. Let's do another one. Use the Laplace transform to solve y double prime plus 2y prime plus y is equal to 4 e to the power minus t, with the initial conditions y of 0 is 2, y prime of 0 is minus 1. This one I'm going to go through very, very quickly. What do? First, we have the differential equation, and we take the Laplace transform of everything. Laplace transform of y double prime plus 2 times the Laplace transform of y prime plus Laplace transform of y plus Laplace transform of 4 e to the power minus t. On the right-hand side, Laplace transform of 4 e to the power minus t is just 4 over s plus 1. Next, I want to look at the green term, Laplace transform of y prime. We know what that is. Look at the orange term. We know a formula for the Laplace transform of y double prime. So here it is. And then next, I want to use the initial conditions. Y of 0 is 2, y prime of 0 is minus 1. Let's put these numbers in. And then we want to start rearranging so that we get y equal to something. Gather all of the y terms together. This part, minus 2s plus 1 minus 4, I want to move this all over to the right. I'm going to factorize s squared plus 2s plus 1. And I'm going to put the whole of the right-hand side over the same denominator. And then I'm going to take the s plus 1 squared and I'm going to move it over to the right. We found capital Y. We need the inverse Laplace transform of capital Y, because the inverse Laplace transform of this function is the solution to the initial variable. So the next thing to do is to use partial fractions, and I'm going to leave it for you to check that we need to have A is 2, B is 1, and C is 4. So I'm going to leave it for you to check that this function can be written as 2 over s plus 1 plus 1 over s plus 1 squared plus 4 over s plus 1 cubed. And I'm going to split that up like this. 2 multiplied by 1 over s plus 1. 1 over s plus 1, look at your table of elementary Laplace transforms, you'll find it there. 1 over s plus 1 squared, again, you will find that on your table of elementary Laplace transforms. But you will not find 1 divided by s plus 1 cubed. On the table of elementary Laplace transforms, you will see that there is a 2 divided by s plus 1 cubed. So I'm going to leave the 2 inside the final bracket, and I'm going to take just 1 factor of 2 outside. Looking at your table of Laplace transforms, you will find that the Laplace transform of e to the power minus t is 1 over s plus 1. The Laplace transform of t, e to the power minus t, is 1 over s plus 1 squared. And the Laplace transform of t squared, e to the power minus t, is 2 over s plus 1 cubed. These are the ones we need. Therefore, the solution to the initial value problem, I'll leave this for you to check, we can find is 2t squared plus t plus 2 multiplied by e to the power minus t. And again, I can show you a graph of this function. Another example. Use the Laplace transform to solve. This time we have a 4th order differential equation. 4 derivatives of y plus 2y double prime plus y is equal to e to the power 2t with the initial conditions y of 0 is 1, y prime of 0 is 1, y double prime of 0 is 1, and y triple prime of 0 is 1. Okay, we need some space. Here's the problem at the top, the differential equation and the initial conditions. What do we do first? First, we take the Laplace transform of the differential equation. There we go. And then we need our formulae. We need the formulae from the theorem about how to take the Laplace transform of derivatives of a function. And we need to look up the Laplace transform of e to the power 2t on our table of elementary Laplace transforms. Once we've done that and we've substituted in, we get to this point. Next, I want to use the initial conditions. All of the initial conditions are equal to 1. So we get this equation. Let's start rearranging this equation. Gather all of the capital Y terms together. These other terms on the left, I want to move all of these over to the right. And then I want to put everything on the right as over s minus 2. I'll leave it for you to check that s cubed is the same as s to the power 4 minus 2s cubed divided by s minus 2. And I'll leave it for you to check the other terms. For example, check that 3s is the same as 3s squared minus 6s over s over 2, and so on. Let's simplify this a little bit. That's the same as s to the power 4 minus s cubed plus s squared minus 3s minus 5 over s minus 2. And next I want to take the s to the power 4 plus 2s squared plus 1 and move it over to the right. And then it's time for partial fractions again. And this time I'll just tell you the answer. I'm trusting that you know how to do partial fractions. Check later that I didn't make any mistakes. Please check that this is what we get when we use partial fractions. We need to break this up into things which we can find on the table of elementary Laplace transforms. And I'm choosing to break it up like this. 1 over s minus 2 I can find, s over s squared plus 1 I can find, 1 over s squared plus 1 I can find, 2s over s squared plus 1 all squared, I can find that there, and 2 over s squared plus 1 all squared I can find. And then we're left with the other numbers outside of the brackets. Now, note that the Laplace transform of e to the power 2t is 1 over s minus 2. We'll need that. The Laplace transform of cos t is s over s squared plus 1. We'll need that. The Laplace transform of sine t is 1 over s squared plus 1. But what do we do with the last two? How can we find the inverse Laplace transform of these last two? Well, that's the key part of this example. Let me remind you of a formula from the last lesson. The Laplace transform of t, f of t, was minus capital F prime of s. We're going to be using this to find the Laplace transform of t sine t and t cos t. First, let's look at t sine t. Using the formula, that must be the same as minus the derivative of the Laplace transform of sine t. Minus the derivative of 1 over s squared plus 1, which is 2s over s squared plus 1 squared. And does that look familiar? Yes. So that's the first one taken care of. Now let's move on to looking at t cos t. That must be minus the derivative of the Laplace transform of cos t. That's minus the derivative of s over s squared plus 1, which is 1 over s squared plus 1 minus 2 over s squared plus 1 squared. Now that's not exactly what we want. We wanted to get 2 over s squared plus 1 all squared, and we've had this extra term. There's a minus sign in the middle as well, but that doesn't matter. We can just move the minus sign over to the left. That's not a problem. We need to remove this extra 1 over s squared plus 1. But what is 1 over s squared plus 1? 1 over s squared plus 1 is the Laplace transform of sine t. So next, we're going to be looking at the Laplace transform of sine t minus t cos t. Because then the 1 over s squared plus 1 terms are going to cancel. Minus will cancel with minus, and we'll just end up with the term that we want. We'll end up with 2 over s squared plus 1 squared. Okay, so these are the functions that we want. We want t sine t, and we want sine t minus t cos t. Let's go back to the formula for capital Y. Now that we have these two new formula. Capital Y is this, 1 over 25 multiplied by an orange function plus 24 over 25 multiplied by a green function plus 23 over 25 multiplied by a red function plus 9 over 10 multiplied by a dark blue function plus 4 over 5 multiplied by a light blue function, a cyan function. And we know what all of these colored functions are now. So we can take the inverse Laplace transform and see that small y is 1 over 25 e to the power 2t plus 24 cos t plus 23 sine t. That's the first three terms. And then for our last two, that's 9 over 10 t sine t plus 4 over 5 sine t minus t cos t. And I'll show you the graph of the solution to this tricky problem. Okay, so that section was mostly revision, but I did put a difficult example in at the end. For most of this week's lesson, or for the rest of this week's lesson, I should say, I want to talk about step functions. And we start with the unit step function, which we denote by UC. This is the function which is equal to 0 if t is between 0 and some number c, and then it jumps up to 1, and from c all of the way to infinity, the function is equal to 1. For the rest of today's lesson, we're going to be using this function. So memorize this graph, memorize this idea. First, it's equal to 0 until we get to c, and then it goes up and it's equal to 1. Draw the graph of y is equal to 1 minus uc of t. Oh, here it is. First it's 1, and then it goes down to 0. Because 1 minus 0 is 1, and 1 minus 1 is 0. Draw the graph of y is equal to u1 of t minus u2 of t. Now, clearly, t equal to 1 and t equal to 2 are going to be important points for this graph. So what we're going to do is we're going to split our domain up into 3 intervals, between 0 and 1, between 1 and 2, and between 2 and infinity. And we're going to look at the function on each of these intervals. On each of these intervals, it's u1 minus u2, but what are the values of u1 and u2 here? Let's clean this up a little bit. First, let's think about u1. u1 is the function which is equal to 0, between 0 and 1, and it jumps up to be equal to 1. So first of all, between 0 and 1, the function is equal to 0. And then for the last two, between 1 and 2 and 2 and infinity, the function is equal to 1. And then next, let's look at u2. u2 is the function which is equal to 0 until we get to 2, and then it jumps up and it's equal to 1. So for the first two lines, it's going to be equal to 0, and then in the bottom line, it's going to be equal to 1. So we get 0 minus 0, 1 minus 0, and 1 minus 1. But that's just 0, 1, and 0. Let's draw a graph of this. The function is 0, then the function is 1, then the function is equal to 0. Write this function in terms of the unit step function. We have a function which is 2, and then it's 5, and then it's minus 1, and then it's 1. Now, let's look at the first number. First, we have 2. So the function is going to be 2 plus something. That takes care of the first part of the function. What happens when we get to 4? When we're at 4, we go from 2 to 5. We go up 3. So in our function, we're going to do plus 3 because it's going up, and u4 because the change is happening when t is equal to 4. That's the first part of the function, and then it's still going to be plus something because we haven't taken care of the end of the function yet. The next change happens when t is equal to 7. When t is equal to 7, we go down 6. From 5 to minus 1 is down 6. So minus 6, and because the change happened at t is equal to 7, we multiply that by u7. And still it's plus something because we haven't finished yet. There's one more change. A change happens when t is equal to 9. At 9 we go up 2. So we have to add on plus 2 u9. And then we're finished. We have our function is 2 plus 3u4 minus 6u7 plus 2u9. Let's look at a more advanced example. Write this function in terms of the unit step function. Function is equal to t, and then it's t minus 1, then it's 2 minus 2, and then it's equal to 0. Here's a graph of this function. We've got 3 changes or 3 jumps, and these happen when t is 1, t is 2, and t is equal to 3. So we know that the function must look like this. We start with t. The first part of the function is t. We have a change or a jump at 1, so plus something u1. There's another change or jump at 2, so plus something u2, and then plus something u3, because there's another change happening at t equal to 3. At each one of these jumps, or each one of these changes, we're going to calculate function on the right minus function on the left. Let's look at the first jump. On the right of the first jump, we have y is equal to t minus 1. On the left of the first jump, we have y equal to t. So for the first jump, we do t minus 1 minus t, and we get minus 1. Next, look at the second jump. At the second jump, there's t minus 2 on the right, t minus 1 on the left, so we do t minus 2 minus t minus 1, and again we get minus 1. Now this makes sense because we go down 1, but the shape of the function doesn't change, the slope of the function doesn't change. Next, look at the third jump. Again, we're going down, but we're not going down to this diagonal function. The function is changing here, so this is not going to be just minus 1. At the third jump, on the right we have 0, and on the left we have t minus 2. So the third jump needs to be 2 minus t. And that's what we need. Therefore, we can write that this function is t minus u1 minus u2 plus 2 minus t u3. Let's do another example. Write this function in terms of the unit step function. Here's a graph of this function. First, we have t squared. So the function we're going to write is t squared plus something. There's a change at 2, and the function becomes 4. There's another change or jump at 3. And then the function becomes 4e to the power of 3 minus t. This function doesn't have discontinuities here, but the function is changing its formula here. So I'm still using the phrase jump. F of t is going to be t squared plus something u2 plus something u3. What are these somethings? At each one of these somethings, we do function on the right minus function on the left. So for the first jump, it's 4 minus t squared. And for the second jump, it's going to be 4e to the power 3 minus t minus 4. Okay, so we can use the unit step function to write our piecewise defined functions like this. But what is the Laplace transform of the unit step function? Let me remind you of the definition of the Laplace transform. I've written this at the top. The Laplace transform of small f is the integral from 0 to infinity e to the power minus st f of t dt. We're going to use this definition to find the Laplace transform of the unit step function. So we have the Laplace transform of uc is integral from 0 to infinity e to the power minus st uct dt. Now remember, what does the graph of the unit step function look like? We have a function which is equal to 0 until we get to c, and then the function is equal to 1. So we're going to get 0 if we're between 0 and c, and then we're going to get 1 if we're between c and infinity. And of course, integral of 0 is 0, so forget about the first one. We have the integral from c to infinity e to the power minus st dt. We know how to calculate this. This is just e to the power minus cs divided by s. This is an important formula. We're going to be using this a lot, not just today, but also next week we're going to be using this a lot. So let me write this as a theorem. The Laplace transform of uc is e to the power minus cs divided by s. Let's move on to the next idea. Let's suppose we have some function, any function, and let's suppose we want to shift it to the right. So I just imagine grabbing hold of this graph and pulling it to the right. And to fill in the gap where there was no function before, we're just going to define that to be equal to 0. We're making a new function called g. It's going to be equal to f of t minus c, as long as t is greater than or equal to c. And for the little bit at the start, we're just going to say g is equal to 0. There's another way to write this function. Anytime we have a piecewise defined function, we can define it using the unit step function. Function starts at 0, so it's going to be 0 plus something. We have a jump or a change at c, so it's going to be 0 plus something uc. And what is the change? It's function on the right minus function on the left. So g is uct f of t minus c. Okay, great. But what is the Laplace transform of this? Let's calculate it. Again, we're going to need to use the definition of the Laplace transform. The integral from 0 to infinity, e to the power minus st, uc f of t minus c dt. And remember, this unit step function is either equal to 0 or it's equal to 1. So ignoring the part where it's equal to 0, it's equal to 1 after c. So really we only need to be doing the integral between c and infinity. And then instead of uc, we can just put 1. We need to do a substitution, simple substitution. Let u be equal to t minus c. Then, of course, du is equal to dt, and t is equal to c is the same as saying u is equal to 0. So doing this substitution, the Laplace transform of small g is the same as integral from 0 to infinity e to the power minus s, u plus c, f of u du. Take a factor of e to the power minus sc outside the integral. And then what do we have here? This integral should look familiar to you because this integral is just the Laplace transform of f. This is another very important formula, so let's write this as a theorem. The Laplace transform of uc of t, f of t minus c, is equal to e to the power minus cs capital F of s. We're going to need this a lot, not just this week, but we're going to be using this in particular a lot next week. And I would guess that this is a formula that you would definitely need in the second midterm exam. So, for example, find the Laplace transform of this function. T, then t minus 1, then t minus 2, then 0. This is the function that we've looked at earlier today. And we've seen that we can write this as t minus u1 minus u2 plus 2 minus t u3. Now look at the formula at the top. In the formula at the top, we have uc and we have f of t minus c. And these need to be the same. But in our function, we don't have them the same. I have a 2 and I have a 3. I need to change my function slightly so that I make it so that these two numbers are the same. So I'm going to write the function like this. T minus u1 minus u2, the first part, that stays the same. I want to have the same number, so I want to have 3 and 3. And to do that, I end up having an extra term, minus u3. Now I'm ready to take the Laplace transform of this, because I know the Laplace transform of each one of these terms. The Laplace transform of t is just 1 over s squared. The Laplace transform of u1 is e to the power minus s over s. Laplace transform of u2, I know that. Laplace transform of u3, I know that. Laplace transform of u3, t minus 3, we use the formula at the top to see that that is e to the power minus 3s divided by s squared. Let's move on. Find the Laplace transform of this function. The function is equal to sine t, and then it's equal to sine t plus cos t minus pi over 4. Now, this function, we can write it as sine t plus gt, where gt is either equal to 0 or it's equal to cos t minus pi over 4. In other words, g of t is equal to u pi over 4 cos t minus pi over 4. So capital F, the Laplace transform of small f, must be the Laplace transform of sine t plus the Laplace transform of u pi over 4 cos t minus pi over 4. And for the last term, we're going to use the formula at the top. Check. First, we have the same number. There's pi over 4 and there's pi over 4. So we can use this formula. The formula says this is going to be equal to e to the power minus cs, that's e to the power minus pi over 4s, multiplied by the Laplace transform of f, or in this case, multiplied by the Laplace transform of cos t. We know the Laplace transform of sine t, we know the Laplace transform of cos t. So we can just put them in, and this is the answer to this problem. We're going to be doing lots of things like that next week. Find the inverse Laplace transform of 1 minus e to the power minus 2s divided by s squared. We can split this up into two functions, 1 over s squared and e to the power minus 2s over s squared. Inverse Laplace transform 1 over s squared, that's easy, that's just t. Let's look at the second term now. Anytime we're looking to find the inverse Laplace transform of something involving an exponential function, we know that we must be using this formula, this shifting formula that we've been talking about. So it must be u2t, because it's e to the power minus 2s. The Laplace transform of 1 over s squared is t. Replace a t by t minus 2, we get u2 t minus 2. And what is the Laplace transform of e to the power ct f of t? Again, we'll use our definition to calculate this. Integral from 0 to infinity, e to the power minus st, e to the power ct f of t, is the integral from 0 to infinity, e to the power minus s minus ct f of t. That's just capital F at s minus c. We have another shifting formula. Again, it's important, so let's write this as a theorem. The Laplace transform of e to the power ct f of t is capital F s minus c. What would we use that for? We would use that for things like this. Find the inverse Laplace transform of 1 over s squared minus 4s plus 5. This time we don't use partial fractions because the roots of the denominator are not real. So instead what we need to do is we need to complete the square. We need to write this as 1 over s minus 2 squared plus 1. And I want to use the formula in grey at the top of the slide. Note, if capital F is 1 over s squared plus 1, then we have that capital G is f at s minus 2. We're trying to find the inverse Laplace transform of capital F at s minus 2. So we know that we want e to the power 2t f of t. The inverse Laplace transform of capital F, or small f, is just sine t. So we have e to the power 2t multiplied by the inverse Laplace transform of capital F. We have e to the power 2t sine t. So there's two methods that we've seen to find inverse Laplace transforms of functions like this. How do we find the inverse Laplace transform of something like ms plus n divided by as squared plus bs plus c? The first question we should ask is, does the denominator have roots in the real numbers? If the answer is yes, then we factorize it, and then we use partial fractions. If the answer is no, then the technique we want to use is we want to complete the square. and then we want to use this shifting formula. Let's do a couple of examples. Find the inverse Laplace transform of 30s plus 440 divided by s squared plus 32s plus 240. First thing to note is that the roots of the denominator are minus 12 and minus 20. So that means that we're going to factorize the denominator and then use partial fractions. I'm going to leave it for you to check that we can write that capital G is 10 over s plus 12 plus 20 over s plus 20. Why is it like this? Because last year I taught this course on the 10th of December of 2020. So that's why I chose this function. I'm going to leave this example for you to finish. Let's do another one. Find the inverse Laplace transform of 10s plus 12 divided by s squared plus 40s plus 420. What are the roots of the denominator? The roots of the denominator are complex numbers. So we don't want to use partial fractions. Instead, we must complete the square. And I leave it for you to check that after we've completed the square, we get 10s plus 12 over s plus 20 squared plus 20. Again, I taught this on the 10th of December 2020 last year. We want to find the inverse Laplace transform of this function. So let's split this up into easier functions. I split this up into 10 s over s plus 20 squared plus 20 plus 12 over root 20 over s plus 20 squared plus 20. Why did I keep the root 20 here? Because I want it to be the square root of what I have on the bottom. We have 10 multiplied by capital F at s plus 20 plus 12 over root 20 capital H at s plus 20, where capital F is s over s squared plus 20 and capital H is root 20 over s squared plus 20. We know the inverse Laplace transforms of F and H. The inverse Laplace transform of capital F is just cos root 20t, and the inverse Laplace transform of capital H is sine root 20t. So what do we have? We're going to be using this formula, which I'm putting in blue. Laplace transform of e to the power ct, small f of t is capital F at s minus c. And we know that we've broken capital G up into 10 capital F plus 12 over 20. There's a mistake here. There should be a square root just here, multiplied by capital H. So small g is 10, inverse Laplace transform of capital F at s plus 20, plus 12 over root 20, inverse Laplace transform of capital H at s plus 20. Now we use the formula at the top right. Both for F and for H. We have 10 e to the power minus 20t, inverse Laplace transform of capital F, or small f, plus 12 over root 20, e to the power minus 20t, inverse Laplace transform of capital H, or small h. And of course, we know these already, so we can just substitute these in. And that is the end of this week's lesson. Next week, we're going to study two difficult topics: differential equations with discontinuous forcing functions and the convolution integral. And we're going to be, at least for the first one of those, we're going to be using step functions, the ideas from this week. Do you have any questions?